Now, I've said enough good things about language, but also language in all forms, especially English, is not trivial to learn. We have a few examples here. Don is America's most wanted. What's Don? As humans, you know it's Donald Trump. What is America's most wanted? Is he the American citizen's most wanted politician? Or is he just CIA's most wanted? Do people want him in jail? Which one? Manya said both, which is very factually correct. But I'm not saying. Which one is this Times of India trying to tell? Hmm. The people one. Yeah. But actually, she's correct. We have Sunday Times saying all set for the lap dance. What is lap dance? Well, this is actually an F1 Formula race news. And here lap means a run through the entire court and not the ones each one of you are thinking. Dhoni takes the highway, Mahi way. What does it mean? Is Times of India telling that Dhoni took his car and took the highway and went to nowhere? No, it means Dhoni retired. Okay? Chiller proves he is no small change. I don't want to explain it, even I don't know what this means. Okay, so we have these stuff. Yeah, this is what we basically described. Okay, so what is language? हाँ यहाँ से पढ़ के भी बता सकते हो. A way of expressing ourselves, that's right. So language is the only means of communication. Who among you thinks that language is only exclusive to humans? Not exclusive to humans. You're wrong. Language is exclusive to humans. If you see a dog bark, he's just barking without anything. Honestly, dogs do not understand what they bark. There has been study on this. No animal understands language. What they do understand is the tone of the barking. If a dog barks loudly, the other dogs understand that I'm sort of a danger, or I need to fight. Language is, please come in. Language is fairly exclusive to humans and humans only. So, over the period of time, by the way, language is not really old. Uh, how old do we think language is? But for a reference, humans moved, like humans start being humans about 6 million years ago. How old do you think language is after humans started being humans? How long did it take us to figure this out? Ancient scripts are writing. Writing is just 5,000 years old. The first writing pieces that we have, I'm not the best student in history, but due to this course, I had to study a bit of history. The first writing scriptures that we have are 5,000 years old. Language is a bit older. How much approximately? Anyone? Any idea? Any random guess will do. 10,000. Language is a few 100,000 years old. We're not sure how many. It's some X 100,000 years old. But the interesting part is, even after so many years of having developed language, it took us some 100,000 years to develop writing. So evolution has its own ways to work around. Okay. So language is what we use to communicate. What is NLP? NLP is basically we realize that, okay, language is super important. It's one of the core strengths of humans. Humans are the threshold of intelligence as of now. As of now, we do not have such systems which has superseded humans on a global level. I'd say there are systems which has superseded humans on certain tasks, which you might see ChatGPT telling this and that. Okay, GPT-4o was smarter than what, a PhD student, they said. That's false. A PhD student is smarter. You can still pursue PhD. You're not under the AI risk. NLP is basically humans trying to teach computers language. That's as simple as that. One liner. If you get it in an interview, one liner. If the interviewer asks anything else, tell this is all I know. Now, NLP is not a new field, although most of us know NLP from 2020 after 2022 after ChatGPT came out. NLP has existed since 1950. 1950s were a long time when people started realizing that, okay, we have computers. We want to make computers intelligent to some sort. How can we make them intelligent? Make them speak like humans. That's the most natural thing that occurred to us. And you'll see, so NLP is basically a subfield of computer science, artificial intelligence, and linguistics. Linguistics is a completely different field altogether. It deals with the different nuances that we have in language. Computer science and artificial intelligence should be a bit more overlapping, but it's okay. Okay, this is just a chart. It's very colorful. It's not very helpful to us. You'll see that a lot of Indian languages are actually reigning thanks to the population. We have 7,000 plus languages across the world today. What does that tell about humanity on a large? Why do we not have a single language? Cultural diversity. How did it occur to humans to have cultural diversity in the first place? So we get a very core understanding of language from here, which has not been quite explored in the current NLP field, is that language to human brains is not static. Had it been a very concrete static thing, we would all have one language. So to human brains, language is very modifiable. Language is whatever we can communicate with. It has a few structural similarities. If you compare all languages, they have some structural similarities, which are again a part of linguistics that we saw in the last slide. So this is a very core part, which if you go home and if you think about it, is something that current NLP systems could do. Who all are like multilingual among here? Multilingual? Anyone? Everyone knows, right? Almost a lot of people are multilingual, right? We know like at least two languages. Everyone is multilingual. We at least know Hindi and English. Some are even more. So, say I give you a pretty tough problem, right? Pretty complex problem to solve. And it's not like a math problem which you need to, maths is sort of different. You have like formalized rules which you can take to solve it. Some pretty like theoretical problem. And I'm asking you in English, so you will answer back to me in English. Do you necessarily think in English? No, you don't. You think in your mother tongue. That's right. So for humans, language is not a concrete thing. It's like a flow of concepts. Whatever we find convenient, we switch immediately to that. So when you're solving something really complex in your brains, you will naturally switch to your dominant language because that helps with the flow of information. It's fairly similar in large language models as well. Large language models, at some sense, I think we'll go into that in some subsequent lectures. They use these language tokens as highways for flow of information. We'll get deep into that. That's actually a fairly amazing part of research as well. All of us here know about the Turing test as computer science students. If you do not know about the Turing test, it's okay. I'm kidding, it's not okay. You should know about the Turing test. What is the Turing test? Can someone tell me? I saw people nod. I saw people nod. Someone has to tell me now. Who nodded? Okay, nobody's taking the Turing test. It's so sad. You're in an advanced AI class. You should know what Turing test is. Okay, I'm telling. So, Alan Turing was a pretty revolutionary person in the field of AI at large. So, and he was like, he's not like, a recent person. He was one of the early persons of AI around the 1950s stuff. So back then, people were just sort of trying to discover what intelligence is and how can we quantify it in computers and all sorts of stuff. So what Turing said, okay, you know what? Like, have a system. Say, I am sitting here and there's a wall and there's someone else on the other side of the wall. It may be a human, it may be a computer. I try to talk to that other entity on other side of the screen. If I, as a human, cannot differentiate the other one is a machine or a human, we can say that the other one, if it's a machine, it's intelligent enough. Um, okay, is this very relevant today? It is still relevant today, but current systems absolutely smash Turing test. Can you figure out if you are talking to ChatGPT? Like you can figure it out now because we have used so much, we sort of know how LLMs speak. But say like our mother, can she figure it out? Probably not, uh, because they speak better than humans. Let's get real. I do not speak English as fluent and as good as ChatGPT or any of these LLMs does. Okay, so this was about the Turing test. After the Turing test, some companies, the big shots back then, like IBM and stuff, they started making some very crude systems. ELIZA is one of the first NLP systems of the world. What does ELIZA do? It's like a very similar to what we see today ChatGPT systems, but it's a lot more brittle. You can see something like that. It's just very short sequences of text. It is somewhat coherent, but it's really easy to break. Okay, this is universal grammar. You have studied a subject in your third semester, automata. It deals completely with that. I was not good at automata. Again, we're getting back to the same thing, is that NLP is hard. We have some really amazing examples here. Um, Call me a cab. Okay, you're a cab. Such a dad joke there. It's an absolute dad joke. You want you want me to get you a taxi or tell you you're a taxi? Call me a taxi, please. I don't judge. So language is pretty nuanced. Again, we see bank is either a bank which loans you money or it's a river bank. Okay, again, I'll just throw a question at you. How do we as humans figure out when which word means what? Context. Context is really important even in LLMs. We won't go into LLMs today. We'll just go with neural nets. In the next class, or hopefully this week, we'll see the basic structure behind LLMs, and we'll see that the reason why LLMs like sort of was a breakthrough in NLP systems is sheerly because of context. Earlier systems did not incorporate much of this context. The scientists at Google who came up with the structure behind LLMs, they were like, we don't need such complex systems. Just find a system to add context to each of your sentences and voila, you're good to go. And they did that, and now we have this amazing stuff. Okay, I made her a duck. Okay, so we have another few nuanced examples. You can go through them, have a little laugh, although these are barely funny, but okay. Okay, so what are the fundamental sort of subatomic parts of language? Words, right? Words form a subatomic part of any and every language. Every language has words in common. How they represent it, it's sort of different. The way we write a word in English is fairly different from how you'd write a word in Mandarin. But all languages, as far as I know, have sort of a structural similarity to what a word means to us. It's like there are singular tokenized structures, which, when formed in a sentence, means like, portrays some meaning. Okay. Okay, who would like to read this for me? Yes. What does that mean? That's the right answer. Even I don't know. It's yeah, no, I'm not trying. Is it a valid sentence though? Yes. Because if you cannot tell from this picture, it's a ship shipping ships, shipping ships. I bet you couldn't tell from this picture. Okay, so again, let's go into a few nuances of how language works and how it is. So, like Alok said there, context is really, really important. The bark of the dog was loud, and the bark of the tree was sappy. As humans, I don't need to tell you, like, hey, that bark is different from this bark. No, I don't need to tell you that. You all are intelligent, sentient human beings, right? So you know what context means because from childhood, you have sort of built your brain up in the way how context works. So you've read so much stuff through your life that now, naturally, when you look at certain stuff, you know what they means without having to really squint your eyes at them and try to figure out in your brain. Okay, I'll just go into another important stuff here. We know context is important, right? How do we figure out the context of a word? What's important for figuring out the context of one word? Reading the words before and after. That's right. Reading the words before and after. Once again, I'd like you to note this down in your brain and highlight this real bad because this is another very fundamental concept of how LLMs work today. I'm just, sort of giving you a little spoilers so that we can build up to that. Complexity of grammar and syntax. English language, I think, again, as far as I know, is one of the most nuanced languages out there. There's a lot of grammar, lot of syntaxes, lot of this, that, linguistic parts. Multilingual, I can't speak. Multilingualism. All right. Multilingualism is, what is it? Anyone? So basically, we have a concept in our brain. A concept necessarily does not need to have a language. We do not know how it really works in the human brain, this part of a concept. You can imagine as sort of an abstract structure inside your brain. Language is simply a tool to communicate that context to the one in front of you. Say you are on your first date and your date, she or him, is on Bumble. They looked really nice and you had a good talk with them, and now you're on the date, and now you turn out it so turns out that they are actually not such of a good person. Now you want to leave from there. You want to pick up your phone, call an Uber, and just leave. A lot of things are going inside your head at that moment, right? Is it necessarily all of it combined in a language as long as you're trying to speak to that other person? No. It's sort of an abstract space where you have these certain concepts roaming around, floating around in your head. And whenever you need to communicate a certain concept, you'll just figure it out in sort of a specific language. Sorry. Okay, this is also the sole reason some people are good speakers and some are not. What makes a good speaker and a not so good speaker? How well they're able to translate this concept from their head to the audience or whoever there is. So this is actually a fairly good example of making you believe that there is some sort of abstract concept which goes on in our head. For humans, this abstract thing is actually fairly nuanced. For computers, it's not. We have such systems lately. I think last year, December, or this year, January, Meta released a paper named Large Concept Models, where large language models are next token predictors. We learned the last day. What Meta did is that they said, this is not how humans work. We do not do next token prediction inside our brains. We somewhat do a next concept prediction in our brains. So Meta sort of wrote a paper that we can also do this in computers in sort of structures. And LCMs are super interesting thing. Maybe I'll refer you to that paper if you want to read it. Okay, moving on. Okay. Again, we have, these are all like the different structures and nuances of language. Bill paid the bill, Paris is a popular name, Apple released a new iPhone. We all, as humans, as English speakers, are fairly comfortable with this. But suppose you pick up a Vietnamese person who is not very strong with English and you tell them that Bill paid the bill. They're going to slap you, I promise you. Vietnamese people will slap you if you send them Bill paid the bill. Because for them, it does not make sense. How are you using the same thing in the same sentence in two different contexts? Does it mean that Vietnamese has no sense of context? No, but maybe their sense of using context in a language is different. And yes, this is real. Some languages have different ways of using context in them. So the way we use context in English is fairly different the way French people use context in French. Like there's a pretty famous example. We have a car company named BMW, right? How do you spell BMW? If you see a BMW car and your friend is there and he asks what car is that, what do you say? BMW. That was a BMW. Which now to all Indian speakers, English speakers, it's BMW. BMW is a German car. If you go to Germany and you say it's a BMW, they'll get really angry and they'll say it's not a BMW, it's a BMW. Beigische Motor and Werke. So it's not a BMW, it's a BMW. So BMW is correct, BMW is correct. If you go to bmw.com website, they have an entire page on how to speak BMW in different languages. They have it in English, in French, in German. So, language is fairly important to multi-billion companies too. So again, these are, just basic NLP building blocks of how language is built up from ground. There's something called morphological analysis, syntactic, this, that. There are different parts of a language. There's a POS and EOS, and NER is, what you see, NER is named entity recognition. I'm not sure what WSE means. Okay. Pronunciation, everyone is sort of comfortable. I'm not going into that. This is not very, related to our field. Tokenization is a super important part. We sort of looked at it the last day. Here we see that how are these tokenized? As words or as like what do you say, punctuation marks, right? Tokenization in large language models is also important, but we do not tokenize it as words as you see this way. The ones who were present in class last day, I showed them how tokenization is done in GPT-4o. It's a non-deterministic sort of process to us, although that is tokenization in LLMs, I mentioned the last day, is also a process which is trained on our data, but it's not like how neural networks are trained. It's a different sort of training. Okay, so in the last class, we saw that in the early 1960s and 70s until sort of the early 80s, language modeling was all about statistics. We had bigram models and trigram models where all you did was you trained it again on a relatively large corpus of data. And then what does a trigram model do? You also have the Colab notebook that was shared. If you went through it, you sort of have an idea of how that works in code. It's basically for a word, you look at the last two words and you try to figure out how many times have you seen this context in your training data? And based on that, you're trying to figure out what the next word is. Now, imagine if your brains work like this. I'm speaking a lot of stuff. If you could only remember the current 3 words that I spoke, just the latest 3 words, would you have a lot of understanding of what I was telling? No. So statistical methods at some point of time fall weak to this. They do not have enough context in them to sort of imbibe meaning in the language. And hence, that's where we sort of shifted to this paradigm of neural language modeling. What does neural language modeling mean? We take that same n-gram, bigram, trigram concept and we try to scale it up. How do we scale it up? With neural networks. This architecture that you see here, this was from a paper from 2003. It was from Yoshua Bengio. If you do not know who Yoshua Bengio is, he's sort of a father figure in the field of NLP, NLP AI today. And he proposed this structure in 2003. He said that basically what we are doing with statistical structures, you can take that, take a neural network. Okay, let me sort of go through it, what's happening here. These are WTs are words, right? And you have a sort of index for each of these words. You feed these words to a neural layer. What do these layers do? These layers embed the words onto a higher dimension. We'll get into more depth into why embedding words into higher dimension is so important. And why even as humans, we do it without the knowledge of doing it. This allowed models to learn high dimensional representation of each word. And this point allowed us to get better probability of word sequences. Why? Okay, I'll just show you something. ऐसे escape करने से ये होगा ना minimize या you can really go through Chris Ola's blog. Okay, where did we come? Oh, blog, yeah. Christopher Ola is a co-founder of Anthropic, Claude AI that you use these days. He is a founding figure in the field of mechanistic interpretability in AI. Mechanistic interpretability is one of the toughest fields in AI research. What it tries is, we all know that neural networks are sort of a black box to us. We do not know how they really work in the insides. Mechanistic interpretability is a field which sort of tries to figure out how it works. So if we go to this is all of the blogs here are amazing, by the way. And I just like to show you what we mean by projecting words onto higher dimensions and how that's any useful to us, if Kit Internet allows me to. So I can. Okay, yeah, we're good. What does higher dimensional mean, first of all? Again, last day, the ones who were present in class, we sort of played around a bit with PyTorch. We saw how we can extend matrices to higher and higher dimensions. Okay, for the ones who were not there, what does higher dimension mean? It's basically, you know about how matrices work. Um, a vector is a 1D array. 1D means one dimensional. A matrix is a two-dimensional array. Anything greater than that is an n-dimensional array. What does that mean? Is that we are storing information in multiple dimensions. We humans live in a three-dimensional world. Everything around us is three-dimensional. There are multiple dimensions beyond three as well. There's an entire field of mathematics which deals with this multi-dimensional thing and how shapes and stuff sort of, move around in that high dimensional space. So it so happens that you can take a word, see, you can take similar and words, and you can take it and project to a multi-dimensional space. Say you take similar and encode it somehow and project it to a 700 dimensional space. When you do that, very interesting properties emerge. Like this is an amazing example. Um, I'm not exactly sure, but Mikolov et al. Is probably from a paper named Word to Vec. I might be wrong. Or you know what, I might be correct. So Word to Vec, we'll go through Word to Vec in probably the subsequent lecture. They figured out an amazing thing. They took languages and they projected some words onto higher dimensions. And what they saw was that when they projected man and they had the vector of it, that vector was exactly perpendicular to the dimension of woman. So somehow in higher dimensional space, we know that the concept of man and woman is exactly contrary to each other. It's like perpendicular to each other. They are sort of in the opposite directions. Even more interestingly, the vector of uncle and aunt was sort of in the same direction as to the vector which pointed at man and woman. So not only does high dimensional space have an understanding that man and woman are sort of polar to each other, it also knows that uncle and aunt are aligned in the same way. Because uncle is sort of similar to the concept of man, and aunt is similar to the concept of women. Same with king and queen. So we found this amazing properties is that when words are projected to higher dimensional space, the mathematical space of those words starts compressing some sort of meaning in them. How does it happen? Through lots and lots of data. The first time I read about this, I was like in my second semester, and I kid you not, my brain was blown out. I was like, how is this happening? This is false. They're fooling us out. This cannot happen. But it so happens that when you give a lot and lot of this data, it's just like maths is so amazing. The math can figure out from that data is that, okay, these words, man and woman, king and queen, they are interacting in the same way like aunt and uncle. So all you have to do, okay, in any sort of AI that you study, one of the fundamental qualities that you can have is try to imagine everything in sorts of linear algebra. So everything in sorts of matrices and how they interact. So with enough data, the maths can figure out that these vectors are aligned in the same way. Does anyone remember how eigenvalues and eigenvectors work? You learned in your first semester, probably have forgotten. So if you ever delve deep into AI again, and you have to study what eigenvalues and eigenvectors are. Basically, their eigenvalues and vectors are very aligned to each other. How does this happen? Again, magically, only through data. With enough data, the maths is somehow sort of able to figure out these relationships among all of these stuff. And this is what we mean why projecting words onto a higher dimension is so important. Because magically out of thin air, now you can teach models to have a sense of meaning in the words, the same meanings that you have. Why? Once again, because language is formed by humans and humans are intelligent. Language have a sort of structure in them which we just take for granted, but deep down in the mathematical space, it's very, very pronounced. And these are all the magic that we get from all those structures. All right, so before going into neural language modeling, we'd like to know what neural networks are. Who knows what neural networks are? A raise of hands, please. Nobody knows what a neural network are. That's the right answer. Even I did not raise my hands. Nobody knows what neural networks are. I can teach you, and I can teach you pretty accurately. I'll not teach you anything wrong. I'll not give any false information. And yet, none of us will know how neural networks are and how they work. Because, why? We humans only know to deal in 3D data. We have never seen anything more than 3D in life. We have no idea what a 4D space is even, let alone high dimensional. Neural networks work in thousands of dimensional space. How do you even think of interpreting what these models are doing? So if any of your friend tells you that they know what a neural network is, smile at them and tell them, no, you don't. Okay. What inspired the origin of neural networks? Anyone? That's right. Mania is really quiet, but she always gives the right answer. Exactly. It's modeled after the human brain. What a fun paradox is that we do not know how the human brain works either. So you're trying to model something out of something which you do not know how it works. But neural networks do work, and we have long shifted from this mindset that we are trying to model neural networks from the brain. But the way it originated in the 1950s, if you again study history, you'll see the first origination of a neuron was by a scientist named Rosenblatt. And Rosenblatt proposed something called a perceptron, which is analogous to a simple human neuron. A perceptron is also somewhat what we use as a neuron these days, except it was just a toy model and it was not very powerful, right? So, okay, this is exactly what a neuron is. You have some data, you feed it to a neuron, the neuron performs some processing on it and outputs some data. What's all this processing that's going on? Multiplication and addition. That's all. Nothing complex. Just multiplication, just addition is all it takes. Just multiplication and just addition is also what happens in ChatGPT. So if you're seeing, and if you ever take a step back and you do not take these LLMs for granted and you see how amazing they can speak, they're just doing multiplication and addition beneath all the systems. So multiplication and addition can sort of solve your tests today. So what we do is take some data, we take the sum, that B you see is a bias. We'll see what bias is. Explaining the bias is actually sort of a nuance. What the bias does is basically it sort of shifts the data left and right without changing the. Let me figure out my words. What the weights are doing is imagine a space of data. Close your eyes. Imagine there's a space of data. And you're trying to mold your data into such a way, trying to stretch it, squeeze it, pull it in such a way that it's useful to you. What this weights does is that it folds and stretches and sort of modifies the data. What this bias does is just move the data around. It does not fold or stretch the data. If I have a folded data here, it will just shift it here. Because in the data space, I need my parameters of the model. By the way, these are the parameters of the model. The weights and biases are the parameters. What do we mean by parameters in a neural network? We simply mean that these are our knobs. Imagine a neural network is a radio, right? And you're trying to tune it to a specific channel. Well, now, I don't know, nobody uses radio, but we are not that young that we don't know what radios are. You sort of, tweak the knobs there, and it's a really fine tuning. It's like you have to see this, and suddenly, samachar aapka, that's that. And from like a really noisy channel, you get into a good channel. That's exactly what happens here. You have a lot of noisy data points, and you're trying to find the good spot in the data space. These are your knobs. You have millions and billions of these knobs. These are your parameters. So when you hear neural networks, LLMs are like, Llama is releasing 8 billion parameter model. They're basically telling that in our neural network, we have 8 billion of these knobs. And during training, the neural network is trying to tune each of those 8 billion knobs to give you an output in the best way that it can. Cool. Okay, so the key stuff that we saw, these are the inputs, these are the parameters, and this is sort of the math that's going on. If you break it down, a neuron is actually nothing. It's a concept. We're just doing addition and multiplication over time. We'll see what iteration functions are and why they are super important later today, not next day. So we have inputs, we have the parameters. What are the inputs? Say, whatever you feed to ChatGPT is an input to ChatGPT. ChatGPT is already trained. It's a trained model. So the people at OpenAI took a lot of time and a lot of hard work to fine-tune these little knobs inside the neural network. LLMs are neural networks as well. They're just really, really huge neural networks. So you tune these weights and biases, the parameters of the network, just to the right setting, such that they are speaking just like the way we want them to. And again, like we said, activation functions, we'll see what all of this non-linearity and stuff means. Okay, we have reached MLP. When we tell neural networks, this is the first thing that comes to our brain. This is what, if you read any blog on LinkedIn or whatever, introduction to neural network, they'll use some sort of random picture like this. This is a specific type of neural network. This is not what neural networks mean. This is a type of neural network. Can I tell that you are what humanity means? No, you are one human. This is one type of neural network. This is not the entire neural network paradigm. But also this works in the same way. You have these inputs, and all of these little arrows that you see are basically your weights. You have the input, you multiply it with the weight, you get some more inputs, and then this process goes on. It's like data flows from here to here. At each stage, it's just multiplying the input with the weights to get some output. Oh, let's see. We have input and we have some weights. This is a number, these are numbers. Everything is number. Floating point numbers, okay? No integers. We have input, we have base. Okay, once again, interesting question. In neural networks, do we all know that we use floating point numbers? It's okay if we don't know. Some of us, we are here to learn. In neural networks, we use floating point numbers. All good? Everyone knows what floating point numbers are? Okay, I'm not interested. Why? Have you ever asked yourself, why are we using floating point numbers? Although, again, in your first semester, you've studied in your C classes that floating point numbers are take more memory than int. Int का कितना byte होता है? Floating point का? So why are we taking more memory?
Precision.
What does that mean?
Like the data will be more accurate, so number of placements.
That's it. Int does not have a lot of precision to deal with. 7th के बाद 8 ही आता है. But I do not, maybe the neural network does not want to take such a large step. Maybe if it's at 7, it will just go to 7.0001. So we need that precision, hence we use floating point. Interesting thing, if you ask to your people, I have asked this question multiple times when I've conducted neural network sessions. Most people don't answer. Okay. It's really important to have intuitions about everything. Can I just move this one? So, okay. All good. Huh? Okay, yeah. What's a neural network? At its core, it's just a function. What does the function do? Mathematical function. Or a computer function, they sort of all the same. They take some input, give some output. Right? Neural networks work the same way. You give it some input and it gives you some output. So, on a very high level, we can say that a neural network is a function, mathematical function. Give it some input, it gets some output. It consists of multiple neurons arranged in different layers, like we saw in NLPs. A neuron in layer N tries to further modify and align the outputs of the previous neurons in layer N-1. What does this mean? Basically, I'll show you a very good visualization of what this line means towards the end of the lecture. But till then, I told you that in the data space, I'll reword myself a bit because we are all studying advanced AI. So we are already some sort of scientists. So I'll use proper science terms. We do not tell a data space. In proper science, we call it a data manifold. In a data manifold, kuch nahi hai. Data manifold is, close your eyes, imagine a square, and that's like basically, okay, you know what? It's a bit difficult for you to understand. Say I am a parameter, okay? And this entire classroom is my data manifold. I need to be at a specific place in the classroom for the neural network to work correctly. Only if I'm on that tile will the neural network be able to work correctly. So, what these layers do is basically at each and every layer, each and every neuron is trying to tune the parameters in such a way is that the parameters are in the right spots in the data manifold. Say all of you are parameters and I want you in specific spaces. I do not want you to be on top of that. Because that's it. I want you to be seated here. I want you to be seated exactly here. I want you to be seated exactly there. And so each one of you, if this class is a neural network, each one of you are the parameters. You are in your right place now. If any of you change your seats, the neural network will collapse. Because it's very sensitive to each one of you, and each one of you are important to the neural network. And to me, each one of you are important to me as well. each neuron is trying to modify the data manifold in such a way that the mapping gets easier for the network. Again, the same thing I said. This is slightly difficult to understand if I'm saying it. I'll show a visualization, which will make it a lot easier. But again, what I'm basically trying to tell is the data manifold is a simple space in which the parameters of a neural network exist. So what a neural network does is all it tries that each one of my parameters will be on the right space in the data manifold. That's what all of these layers and neurons are trying. Okay, so let's say this is our data distribution. Okay, this is class 1, this is class 2. We want to classify the two classes. All good? Let's assume a very simple neural network, something like this. You have an input layer and you have an output layer. Okay, you have the input, you have very few weights, you just perform some minor transformations on that input and you get that out. With such a simple neural network, this is sort of the classification you'll get. Just a straight linear line in your data manifold. But is this very useful to us? No. Why is this not useful? Bolo, bolo, speak loud. That's right. You speak loud. Even if you're wrong, something I said in the last class, I'll tell it again. All of us who are teaching are researchers in this space. What do researchers do? We sit all day and we ask the dumbest questions and we try to find the answer to that. So we always encourage asking dumb questions, because the dumbest question you probably will ask is, in my experience, the most interesting question that can be there. So, ask dumb questions each time. So with such a simple thing as, what's your name? As Shreya said, you only get a linear mapping of it. But this is not useful because the data is curved. What will we do with the linear mapping? What do? You add more layers, you add more neurons, you add more parameters. And with this setting, with an intermediate layer of neurons, now you have the input layer in blue, you have the output layer in green, and you have a hidden layer. This is an extra set of processing. You're giving more processing power to the neural network to sort of classify the data. And when you give this, the neural network can now sort of find this smooth curve around it. We will see how this happens. This happens due to what we read as activation functions. It's because data in the real world is not linear. Do you think linearly? No. Do you? Does someone think that they think linearly? No, you're not. We are pretty complex beings, and neural network is not even half as complex as what the human brain is. So let's take a moment to appreciate the human brain. So when the data is not linear, there is no point in the neural network's outputs being linear. So we need to find some way to make them such non-linear. Okay, if you give it more power, then the neural network will entirely modify this data manifold, and you need a bit of imagination to walk this through. But this same thing is in 2D. If you imagine it as 3D, these lines are the same curves we saw in the last one. The neural network has simply squeezed and modified the space in such a way that now it's able to find a linear mapping through the data manifold, which exactly classifies the two. You'll see that in 2D space, we can do this. But if we project it to a higher dimension, we can find a space in that higher dimension where this data is linearly separable. So again, let me reiterate on how important higher dimensional spaces are. It's because neural networks, since they work in such high dimensional spaces, they're really good at figuring out these data manifolds, operations. How to stretch, squeeze, pull, push the manifold in such a way that I can find an easy way to sort of navigate through my data. Okay. This is another good visualization. Let it get back to normal once, and actually. See, in 2D space, it's not separable, right? You can't draw a straight line which equally separates it. But now I can sort of draw a straight line through here, which will separate these two. At any point in this stretching, squeezing, and pulling, did I break through this two? Did I cut? Did I spread them apart? No. All I did was pull and stretch it. So if you pull and stretch in higher dimensions, you can sort of find straight linear subdividing spaces, even when in 2D it does not appear to you. So amazing things happen at higher dimension spaces. Okay, I went through a bit of the data flow earlier, but it was a really bad description, so I'll go through it in a bit more detail now. Now, instead of just watching colorful little neurons, we'll also see how they work. Neurons are basically numbers, like I said, floating point numbers. So let's say we have our two neuron friends, we have 2.2 and 3.2, and these are the parameters of the neural network. How are the parameters in a neural network initialized? Randomly. Let's say we have some setting of parameters, and we have, again, I need to push this here. Okay. So from 2, we have 2 parameters going. One for this one for this one. One is a 1.5, one is a 2.5. From 3, we have a 1 going to this one and a 3 going to this one. How do we compute the value here? Really simple. Take 2 into 1.5, this one. Just focus on this one. What are the 2 parameters that are coming to this? This and this, blue and orange. So observe the blue one, it's 2 and 1.5. So 2 into 1.5 plus 3 into 1.2. That's 6, if I've not done it wrong. Yeah. Again, for this one, just focus on this one. And what are the 2 parameters coming to it? Red and green. So 2 into 2.5 plus 3 into 3. So that's 4. This is all what happens. Like I said, just multiplication, just addition. That's all what happens in a neural network. There are structures on top of it, but this is always the, basic. Okay, so in the last one, we saw that we were here initially, we did some operations, we got to here. So we are moving in a forward manner. This is the direction of data flow. These are the same 2 neurons we saw in the last slide. So from here, and if you know all of these weights, you can compute your way through here. Any doubt on this? No. You have values, you have weights, perform addition, multiplication, you have these values. Now that you have these values, addition, multiplication, these, addition, multiplication, these. And at the end, you get some output, right? Say this is a neural network which knows how to classify a cat from a dog. Cool. So you have some of these parameters and they're acting in their own way. And then at the end, you get an output which tells, given an image, say this is an image here. This is a numerical encoding of an image. And you get an output that tells, is this image containing a cat or not? This is the forward flow of data. Okay, so you get the output from the last one that we saw. And then you have an output. Say it says it's a cat, but in reality, it's just a chair. So you want to tell the neural network, hi Dumbo, this is not a cat, this is a chair, you're wrong, you're dumber than me, I need you to fix yourself. How does it do that? You have some output, this is the ground truth, sort of the chair thing, and you compute an error. What's an error? It's basically the difference between what the neural network is currently outputting and what we want the neural network to output. I'll repeat that again. Output is what the neural network is currently outputting with its current set of parameters. The last slide once. Oh, okay. These are all parameters, and we saw that all of these values are dependent on these parameters. If these values change, these values will also change. These values will also change. These values will also change, right? And the output will also change. So we compute this error and we tell that, okay, this is how far we are away from where we want to be. And then once we have computed this metric, once we sort of have an idea, say, on an intuitive level, I wrote this as well. It's like you get your exam papers, you see where you made the mistake, and you know how far you were away from getting that 1 mark. So you have quantified that this is how far I was. Once you have quantified, what do? Work on it. For exams, you try to fix that subject. Neural networks work the same way. Once you have the output, that information is relayed back to the entire network. So all of these parameters somehow, we'll see how, have a sense of how I need to adjust myself so I am slightly closer to my original goal. So if it said it's a cat and it was originally a chair, all of these parameters of the neural network will just, these are numbers, right? So they will just tune themselves a bit so that the next time there is a forward data flow, my output is closer to an actual chair and I'm not telling it's a cat. Yeah. This backward flow is known as backpropagation. What an intuitive name. You are propagating back through the neural network. As easy as backpropagation sounds, the difficult it is. It's one of the most difficult parts of understanding, at least. Okay, we'd like to come again to loss functions. So we saw that you compute the error. You sort of have a system which allows you to quantify how far I am away from my goal, right? So you need a function for that. That's your loss function. See the next slide? Okay. Yeah. Loss function is simply the function that you choose to quantify your error. Everyone knows what regression is, linear regression is, right? MSE, mean squared error, is the loss function that you use for linear regression. And it's very intuitive, MSE. Yi is my output, my predicted value, and y hat I is my ground truth. What am I doing? I'm computing the difference between the two. I am squaring it up. Why am I squaring it up? Because for mainly two reasons. One, because squaring it, when I square it, I do not have to deal with negative numbers. I only have to deal with positive numbers. So I can only care about the magnitude of how far I'm getting. When you include positive and negative, it becomes a bit nuanced. But also, square serves another purpose. Is say this difference is very high. The square will amplify the difference. And say you are training the neural network, and each time it makes an error, you sort of slap it and tell it you need to fix it. If the error is large and it gets squared, you'll slap it harder. Uh, Loss functions are an important part. Why? Because for each task that you see, we have a different loss function. We have a different loss function for regression. We have a different loss function. This is the loss function for, this is sort of a generalistic, but this is very close to the loss function that's used for LLMs. So a very interesting thing is, if you study all of this good enough, you will realize that in order to make a model learn something the way you want to, all you need to do is formalize this loss function. If I want the model to act in a specific way, if I want my model to, say, take a specific route of actions, all I need to do is modify this loss function. Towards the end of the class, I will show you something that we did at our RespAI Lab. LLMs work in a certain fashion. Me and my friend wanted to check how it would work in a different way. Data flows in a neural network in a specific way, right? LLMs are more complex structures. We wanted to check that what will happen if we make the data in LLMs flow in a different way. So we literally came up with a new loss formulation for how to train LLMs. And that works. So if you know enough, if you read this enough and you're good at math, you can literally teach models exactly how to learn the way you want. This is a very high level thought. And as for now, just know that loss functions are the measures of how you want to teach a neural network to get a job done. Okay. Okay. Gradient descent. Gradient descent, probably a lot of you have heard. Super important. We saw something called backpropagation a couple slides ago. Gradient descent, and in backpropagation, we saw that the parameters of the neural network are updated after we compute the error. Gradient descent is an algorithm which helps us update our parameters. I'm having to move this over and over. Okay, this one moves. Amazing. Yeah. What does gradient descent do? Say your loss landscape. Now again, what does loss landscape means? It's a lot similar to the idea of data manifold. You have a loss manifold as well. Imagine you are on top of a hill and you want to get down that hill. Imagine this hill is your loss. You want the loss to be minimized, right? So if your loss is a hill, you want to go down that hill. Clear to everyone? Any doubts here till now? No. So if the loss is a hill structure, we want to do something such that we are going down that hill. This is exactly what gradient descent does. Before we come up to this, if you just look at this, this is actually a real simulation of how a loss function evolved in a neural network over multiple training runs. So you see that the loss was here, and this color is basically the gradient of, if you were in class 10, you would have probably studied something similar to topography and geographies. So these lighter regions are shallower regions in the space. The darker regions are higher up. So this point, this is the loss. Overtraining, it's slowly going down the slope. This is what gradient descent does. The gradient of the parameters, how do we compute the gradient? Yeah, that's right. Your loss landscape is simply a space. Your loss can initially be anywhere on the space, and the only point of your training is wherever this loss is, I needed to find this minimum spot. It can be anywhere. It could be here, here, even here, anywhere it is.
Can you also bias it to change the space of the
Yeah. Well, gradient descent does not sort of lead with bias. I'll tell how it works exactly. Bias was for the data manifold. This is for the loss manifold. All of these are sort of different but similar on many levels. These are like slightly nuanced concepts. As you go higher up, everything will slightly seem to confuse up. But a loss landscape is a lot simpler than a data manifold. It's just you have a hill, and wherever you are in that hill, it might not be like a valley. It might be like small hills. There might be small hills here, some down and up again, and some down, all of that. All you need to do is get down the slope of the hill to the minimum point you can get to. Because why? We want our loss to be minimum. We want the error to be minimum. Okay, and how do we make that? By updating the parameters. How do we update the parameters? Basically, you take the gradient of the parameters. What does the gradient of the parameters say? We'll check that out in pretty much detail. The gradient tells is basically, say you have a loss, cool, and you have a parameter. All of these parameters in a neural network we saw are connected to each other. They're all interconnected. So any parameter in the neural network can find its way to the final output and the loss. So what do we want to do? We have the loss, we want to minimize it. So again, first semester, do people remember partial derivatives? Yes. What does dx by dy, not d, del x by del y mean? Reduction, sort of. That del x by del y means that if I change my y a bit, how is that going to affect x? So say I have a parameter w and I have the loss as L. So what does del L by del W means? How can I modify the parameter a bit? How can I tune it a bit to observe how my loss changes, right? And what do we ideally want? We want the loss to go down. So what gradient descent does is that it finds how can I change my parameter a bit such that my loss goes down a little bit. That's what partial derivatives do, right? You change the denominator in such a way that it affects the numerator in some sort of way. That's what we try to do. For each parameter in the neural network, we compute its gradient with the loss, and we tune the parameter in such a way that the final loss reduces. Let's see how that's done in greater detail. Learning rate is basically, again, let's try to see it from an intuitive point of view. You'll see from here it's taking slow steps forward. This is not very fast. If the learning rate is high enough, from here, it might take one big step here, one big step here. It can get here. So, but we don't keep learning rates as high. We keep them as low as 1e negative 5, like 0.00001. That's how low we keep. Why? Because this space is very complex. It's not this simple in real life. So say you are here and you have a really large learning rate, you can just jump right here and it's worse than being here. So you don't want to be really fast. You want to take small, sure steps towards your goal. And yeah, this is basically, now this equation will sort of make sense to you. This portion quantifies how much do I want, how can I tune W in such a way that the loss decreases? This tells you how strongly should I tune it. So this total term tells you the amount that you need to tune W to decrease the loss. And you want to subtract this amount from the previous weight. And doing this gives you your new updated weight. So you have a weight and you have the information. How can I modify this weight such a way that my loss decreases? You subtract the both, you have a new weight. This weight compared to this weight will lead to slightly better output. And we do this over and over and over again. Okay, so yeah, this is one more visualization. This is a more realistic view of the loss landscape. There are multiple, you know, little this bumps and dips in the threshold. These blue areas are dips. These red areas are higher ups. So you start from here, and you ideally want to get here to the lowest point. So you will see that this started from here, the loss, and it's always traveling down this path. Once it has reached this spot, it will start traveling down again through here. In one way or the other, it will try reaching the minimum point in the landscape. Okay, there are a few variants of gradient descent. One is that you can compute the gradient of all of the examples in your training data. You can look at every of those examples and then take a step forward. This is what batch gradient descent does. It computes the gradient from all the training points, and once having done, it takes a single step. How is it good? It's because it has looked at all of the data. It just knows what is the best step I can take. Why? Because like all of the data points is there. It has computed the gradients of all of the points. And since it has looked at all the points, it knows that, okay, this is my full training set. This is the entire data manifold that I have. I can take a step now, and I'll always take it in the most optimal direction. So batch gradient descent always takes the most straightforward path towards the minimum point. What is the downside of this? It's slow because it's having to look at all the data points. That's not very efficient because we can have millions and millions of data points. And if for taking one step, you are having to go through all the million, that's not very efficient. Stochastic gradient descent is exactly the opposite. If you imagine it to be a hill, all of these to be hills, and you're trying to get to the minimum point, batch gradient descent is like a very sane man who is in his sane mind, observing everything around him, taking one step forward in the right direction. Stochastic gradient descent is like a drunk man, terribly drunk. His face is red, he's so drunk. He will take steps in whatever this and that direction he wants. Like he sort of has an idea that, okay, I can sort of see where the minimum is, but it's very bloody. He can't really see where it is. So he'll just, fumble around a bit here and there, here and there, here and there. But eventually it will get to. It will take more. See, here it's like 1, 2, 3, 4, 5 steps. Here it's 1, 2, 3, 4, 5, 6, I don't know how many steps. It's just moving around a lot. It's a lot faster. Why? Because this looks at all of the examples. This looks at only one example and takes a step. Whatever the current example is, it's taking a step based on that. That leads to a lot of noise because each data point is different from the other and their statistics vary. So if you look at one data point and move ahead, is this really going to be that noisy? Mini batch is like a sweet spot between the two. You look at a few data points, take a step. Few data points, take a step. Okay, we'll again get to back propagation. This is where the real math comes in neural networks. Back propagation, what we saw is, just look at here, ignore this for now. We will go into greater depth here in easier examples. Say this is the loss that you have, and this is your parameter. What are you doing? You're computing the partial derivative of the loss with the parameter. Why? You want to tune it in such a way that this decreases. And mathematically, this is a very efficient way to do so. Okay. We'll see how okay, this is a nice visualization of how backpropagation works. You'll see now, it's just moving back through the layer again. And it sort of adjusts something there, and it's again moving forward, and it'll again move back through the network. This backward step is adjusting each of these neurons. Okay, this is a concrete example. I would like to have the attention. Say this is our neural network. Okay, very simple function. We have a function which is nothing but we have three parameters, x, y, and z. And the function is as simple as x plus y times z. Okay. Our job is to find. So the output is the function's output, right? So given the output is, say, the loss. Imagine f as being the loss. So given this loss, these three are your parameters. You want to check how can I tune these three in such a way that my output improves. All good? So this is sort of a graphical structure of the same. X plus y into z gives us f. This is clear? Okay. Now we have the f as 20. What are we doing in back propagation? We are moving from the back. So what's the first thing that we compute? We have f. We know what f is. We know how to compute del f by del f. And that's 1, right? Intuitively, if you think, what does this mean? How can I, if I tune f a bit, how is it going to affect f? Of course, by a magnitude of 1. If I tune f 3 times, it's going to affect it 1 into 3 times. And just, because it gets a bit nuanced, I'm trying to give you the intuition. Okay, so now we have the gradient at this node, and that's 1. Okay? We try to find the gradient here. What is it? I've named it T, an intermediary state. And we are trying to find del F by del P. How can I change this value a bit such that this value changes? How can you do that? How can you express P, F in terms of P? F is nothing but P into Z. So del F by del P is del P into Z by del P. What does that lead to? Z. It's just basically, you need to know your math a bit. P and P sort of cuts out and all that's left. So at this node, what gradient will I have? Equal to Z. That's 4. So what am I going to get here? The gradient at this node? The value? 4. We have the value 4. Now we try to compute at Z. Same thing. Z is F, P into Z is F. So del F by del Z is P into Z by del Z. And this again is P. So here it's 5. Okay? Now we get what are we trying to compute? Del F by del X. How am I changing X in such a way that my F changes? But there is no direct connection to X and F, right? Like Z had a direct connection, P had a direct connection, X sort of has to go through P. So this is the chain rule that you have studied in your class 12. It's a del F by del X can be broken down into del F by P and P by X. This cuts down. This is simple reciprocal, cuts down and is the same as del F by X. We have already computed this part. That's 4. What is del P by X? It's simply an addition, right? This is an addition. In addition, the gradients are always 1, right? If you don't remember, this is it. If you add, the gradients are always 1. So what happens? We know del F by del P, 4, into this is 1. So the value that we get here is 4. Similarly for this one. Because again, you do del F by del P and then you do into del P by del Y and del P by del Y is 1 again. So it's 4. So we just saw how backpropagation works from scratch. This is exactly how it happens. You start computing from here, and you go all the way through your neural networks, computing the gradient for each of the nodes. Is this example fairly clear? Shall I throw a really chonky example that will blast your head off? Let's try. I did not include it here because, okay. Because the OG man has already done it. If you want to really get good, this is where I learned neural networks, by the way. Stanford 231N is originally for computer vision, but in 2016, it was taught by Andrej Karpathy. If you don't know Andrej Karpathy, who Andrej Karpathy is, he is basically one of the most genius people in AI right now. Okay, where are the slides? Videos? No, I don't want that. Five? No, maybe lecture 4. Give it some time to load. This lecture is also was a great motivation while I was preparing the slides. I took a lot of notes from there. So I suggest everyone, and by the way, the videos of these are available on YouTube. So if you go and search Stanford 231N, or if you just search Stanford Andrej Karpathy, you will find the best neural network videos out there. See, it's the same examples we were talking about. You're just trying to get down through a hill. It's for Stanford people, hence there's a lot more math. I have excluded, okay, not 2024. We are going back to 2016. What? Yeah, anyway, I actually, in my computer, the slides were here, but this is Sar's computer, so I need to search up a bit. Anyway, I'll give that as an exercise. It'll really be a super exercise for your brain. But basically, this is a really simplified structure. That example is a lot more complex. It consists of more complex. This is just like multiplication addition. That consists of a lot more functions as well. Exponentiations, there's that, yada yada. Okay. Now, before explaining this, I'll like to go here. You can play around here. This is a playground made by TensorFlow from Google. This is really helpful to understand how neural networks work. Say, this is my data distribution. I have blue points and I have orange points. And I want to classify them accordingly as is. Is this a linear distribution? No, this is a highly nonlinear distribution. Well, there are other distributions which are worse, but let's start with this. Okay. Let's say we have two hidden, let's say we have just an, yeah, it's a very simple neural network. We just have an input layer and an output layer. Okay. Very simple. Let's see how it does. I'll train the model here and you'll see how the model sort of classifies this. This is not a very good classification. All right, everyone agrees? Okay, these are very interesting. You'll get to see what each of these individual neurons are contributing to the classification. So you'll see in this neuron, it's like sort of trying to part it in a vertical manner, some 80-20 way. This one is doing right the opposite. And hence we sort of get this middle structure between the two. So this is not very useful, right? What if we increase the number of neurons? We get a much better structure. How is that happening? See, these are the same. It's just a vertical structure and a horizontal structure. As we add more neurons, you'll see these are still straight lines. This is a straight line from there, here, here, and this is just a random stuff. So if you just observe these three, because see the streams that are going from here, the weights are really high for these ones. It's 3.7, 3.9, 3.7. This one is a lot lower. It's minus 1.5. So this one is not really contributing to this structure. These ones, individually, they're all straight lines. But when you combine the outputs together, you get sort of this structure. And this is basically what I was telling, that individual neurons at each layer take the outputs from the last layer and modify it in such a way that you get these amazing shapes in a non-linear way. Now, you all should ask a question that, okay, all I taught you was these neurons do multiplication and addition. Multiplication and addition are linear transformations. How is it finding a non-linear data pattern? This is where activation functions come. Since data is non-linear, we need to put in some sort of non-linearity in the data training as well. Activation functions help us do that. They inject this non-linearity in the neural network. If I change the activation to linear, you'll see it breaks. The neural network is of no use. And you'll be like, okay, add more layers, add more neurons. Oops. Okay, what? Why is this not working? Change. Okay, well, this part is not working. Anyway, let's add another layer. Let's add more layers here. We can finally add some more layers here. So this is a fairly complex neural network. A much simpler version of this with 10H had already solved this problem. But even with this complex one, with linear, we won't get anywhere. Because all you're doing is trying to find straight lines, how to find through the network, when the data is not even straight. This epoch can go down to thousands and thousands, but this is not getting any better. If I change it to 10H again, you'll see it will crush it immediately. We don't even need such a complex network. You'll see we find all of these very nonlinear shapes as well in the neurons. And at the last layer, we already have these circular shapes. So we know that this neural network is strong enough for this problem. We can also try out the other ones like ReLU. ReLU is also interesting and it's slightly different from 10H. You'll see ReLU has slightly sharper edges around. And I'll show you where this property comes from. But basically, we do realize the importance of activations, right? In my experience on like explaining activations just in slides is very difficult. Nobody gets it. This is the one stop where, you can just play around with this as much as you want. You can go to more complex structures. Like this one is really complex. If you train it, you'll see that it's taking some time, but it's changing over time. It's struggling a bit, But you'll also see that the loss is actually sort of going down. It's now stuck. Maybe for this ReLU isn't the right one. Go 10H and it should work. This is too complex for this neural network. What do? You add some more, you add one more layer, add a few more neurons. Let's see where it takes us. Still not very good, not very fast. We changed the learning rate that we learned. And we sort of see trying to get to a structure, but the loss curve, if you see, it's really nasty. It's not really getting somewhere. Maybe if you play around with it, you will find a solution to it. I found it this morning, but now I can't. Anyway, it's a really nice tool from TensorFlow. TensorFlow is from Google. Really helpful to understand a lot of stuff. Okay. Okay, so these are some of the activation functions, and now you understand how we sort of inject the nonlinearities. Because these functions are literally making your data in a nonlinear shape. You have this straight linear data, you apply these, and your data falls into these shapes. Sigmoid is one of the oldest. TANH is strictly better than sigmoid, which means that you should never use sigmoid and use TANH. This is ReLU. ReLU, do you get why ReLU was having sharp edges? Because ReLU is literally a sharp edge. Swish is ReLU has some problems. Can anyone tell what the problem with ReLU is? Yeah, that's it. Any activation which is negative will fall in here and it will not produce a gradient. So if an activation of ReLU falls in this region, it's called a dead neuron. It's never getting another gradient update and it's just static and dead. It's not contributing. Does it mean ReLU is bad? No, ReLU is the most used activation function is because those instances are really dead. And most of the times ReLU is just really good for you. However, in LLMs, we use none of these. We use something called GELU and is it Swish? No, we use GELU and something called CLU. Okay. What is the problem of overfitting? Again, some of you might have heard. Yes, it basically means that memorizing issue. Someone said in the beginning that memorizing is the same as intelligence. Overfitting is a very humbling concept which tells no. If you just go to the exam, simply mugging up your book without any understanding, will you be able to get good score on the exam? No. Maybe you'll get like passing marks, but not a good score. Hence, intelligent beings, as humans, we are great at generalization. You show a kid two examples of an apple and it'll immediately be able to identify what an apple looks like. So two examples are all we need. So neural networks do that as well. They will find each and every sort of way to mug up the data. We don't want that to happen, and hence we use something called dropout, such that the neural network is not mugging up the data and is actually trying really hard to find the correct way to go through stuff. What does dropout do? You have all these neurons, and during the forward pass, you randomly choose a few neurons and shut them off. So you do not have paths through all of them. How does this help overfitting? It's basically the intuition is that in dropouts, If you use that, you're randomly switching off stuff. So the neural network is not reliant on specific neurons. It just has to generalize through the way. It's like एग्जाम में चिट लेके जाने का कोई वे है ही नहीं. So you have to study because randomly कोई आके तुमको पकड़ लेगा. So that's a nice example to work with. Okay, yeah, we are almost towards the end, right? Okay. Training neural networks is not as easy as you think. Nowadays we have carers for baby neural network learners. If you go a bit above, we have PyTorch. PyTorch is what we use in this class because one, everyone in the industry uses PyTorch, from the largest scientists to all the labs. Two, because I love PyTorch. So neural network training is problematic. Why? Because you have all of this data flowing around, all of these numbers flowing around. They're going through multiple of these activation functions, multiplications, additions, this, that. The numbers are changing constantly, right? What if among these millions of numbers, some number, due to some gradient that flowed through, got multiplied and became a really huge number? Then it's a problem. Because if you imagine the data manifold, if this number gets a really huge update, it will just jump out of the data manifold. What does that mean? It means that the gradient of that becomes so large that no matter how you try to fix to that number, it won't just change. Hence, neural networks like to work with small numbers, anywhere between the range of close to 0, 0.1 to -1 to 1, in that range. Why? Because then the gradients are quantifiable. A gradient comes, you multiply, you do not have a large number. You can tune that again. But if you have a huge gradient and say you multiply and you get to like a number like 10,000, and then the next gradients are really small. So it does not matter if it's 10,000 or 999.999. It does not affect the neural network. But if a value is 0.1 and if it changes to 0.2, it does affect the neural network. So we have to be really, really careful that while training, all of the data is inside a good range. It's just small numbers which the neural networks like. Earlier, by early I mean say prior 2015, neural network like AI scientists had to be really careful with training. They had to be really careful with initializing the values. Even now, we are sort of careful with initializing the values, but we don't manually do it anymore. PyTorch and TensorFlow, whatever you use, does it for you. And they had to be really careful with the learning rate. They had to see that the learning rate was very, very carefully chosen and that you do not choose a big one such that it just takes a huge leap, gets out of the manifold and never comes back. Right? So, in 2015, two researchers from Google came and said, you want nice activations? You want them to be nice numbers? Simple, just make them nice numbers. What's the big? Why did I include this? Is because this is how research works basically. People think that coming up with a new idea is like really, really complex. In hindsight, it's not. Most of the time, it's not. Batch normalization is one of the groundbreaking ideas in neural networks. And this is literally such a simple idea. The authors said, if you want good numbers, if you want them to be in a good range, just make them good numbers. That's simple. So what they do, you train in batches of data, right? Not one. You take like 10 examples, feed it to the neural network, you get 10 outputs. Why do we do that? It's because we train neural networks on GPUs. GPUs are really good at parallel processing. So if you feed it 10 examples, it's the same as processing one example for GPUs. Okay. So you're processing in batches. What does batch norm does? You compute the mean and the variance of the entire batch, the statistics of that batch. Oh, just show the math here. Remove this a bit. Here, yeah, you have this entire batch. You compute the mean of the batch. You compute the variance of the batch. The variance is just the standard deviation squared. And then you normalize each of the data points with the statistics that you computed. How does that help? It helps that in a batch, none of the values are behaving weirdly, because you take the statistic of the entire batch and you ask each and every data point to sort of behave like everyone else in the batch is doing. It's like, say we have a class and we have all of you, and all of you have a different understanding of how neural networks work. Some of you have a better understanding, some of you have a slightly worse understanding. Now, say I come to the class and I tell that I want each one of you to collaborate on a certain project and get it done. How will you do? The ones in the class who are who have a bit more clarity on the subject will tell everyone ki, okay, we don't need to choose very difficult projects because not all of you are as proficient as me. Let's choose something that's slightly beneath my capability. And the ones who are like not so good, they'll be like, okay, there are really good people in this class. I cannot stay like this. I need to study up a bit. So they'll level up a bit. The ones who are really good, they'll level down a bit. The ones who are really bad, they'll level up a bit. And so this is what normalization does. Takes the statistics of the entire batch and levels each one of the points. If some value is really large, it brings it down. Some value is very, very small, it brings it up a bit. That's all batch normalization does. So through the course of training, batch normalizes, stabilizes your values. That leads to better training. What does it do? It improves gradient flow. Why? Because with batch norm, you are having more tame values. With good values, you have a good gradient flow. Allows for high learning rates. Why? Because again, if the training is stable, you don't need to be really finicky with the learning rate. Yeah, reduce strong dependence on initializations, all of that. Now with batch norms, suddenly training neural networks is a bit more easier. You can just throw in batch norm layers at different points of the network and it will automatically stabilize training. Is everything good about batch norm? No, there are some problems. Batch norm computes the statistics for each batch. What if the batch is small? Then the statistics will vary as well. If the batch size is say 4, 4 example को लेके तुम क्या ही statistics बनवाओगे? So if the batch size is 4, then the statistics are noisy. Each batch will have a different statistic. And then each values in that batch will have a different statistic. And they'll get normalized in a different way. So this will again unstabilize training. Neural networks likes all of its parameters to be in a tame range. If the batch size is small, batch norm will just, according to the small batch size, some parameters might be in a slightly bigger range, some in a smaller range. Again, the same issue. We are having unstable training. Also, batch norm has another very weird thing, is that during training and during inference, the behavior of batch norm changes. During training, like I said, you are computing the mean and variance for each of the batch. During inference, which means that after you have trained and you're just inferencing the model, batch norm does not compute the statistics for each of the batches. It just has a running mean and average, which means from the training process, it just takes up some mean and variance and uses it across all of the inference. It does not compute new statistics for each of the batch. So this is another slightly nuance of batch norm, is that it behaves differently during training and inference. Now to fix these, we came layer normalization. Again, very important work in the field of AI. Layer normalization is what's used in current LLMs as well. This is what the authors thought. Batch norm is failing due to batch size. Just don't use batch size. Again, this is what I'm basically trying to say. This is how, like, this is what great research is. You try to solve answers without complicating it. How do you do it? You do not rely on the batch size. Layer normalization is done individual data point wise. You take the statistics of individual data points. Of what? Of the channel dimension. Okay, what does it mean? I said that these data points are protruded to higher dimensions. In higher dimensions, there are a lot of numbers. You take the statistics on this higher dimension channel. This will make more sense when we are studying LLMs. LLMs have a much more specific channel dimension. So that's what layer norm does. In the higher dimension space, it computes the statistics for that data point specifically for its higher dimension and normalizes the data point according to that. And this is also a legitimate way. If you see this formulation, x minus the mean of x divided by the square root of the variance of x is exactly similar to this as well. This is exactly what we are doing. Batch norm and layer norm are not different formulas. They're same formulas applied on different parts of the network. See, xi minus the mean of x divided by the variance plus some eta. Why is this there? So that this, if this is 0, this does not lead to infinite values. That's how simple it is. Layer norm has a lot of good properties. It's independent in batch sizes. It does not have a different behavior during training and inference. Same behavior across. And it's more suited for long context training. What does it mean? LLMs are long context models. You are feeding in hundreds and hundreds of words to LLMs and it's able to figure that out. This is a long context of input that you're providing. Layer norms are very good for that. Is there a problem in layer norms? There wasn't till 4 months ago. 4 months ago, some researchers said that, hey, these layer norms, they're sort of problematic and it's a serious problem. What they discovered is that LLMs have a lot of layers, like we saw, neural networks have a lot of layers. LLMs have a lot of layers as well. Although they're slightly different from the neural network layers we saw. Due to layer normalization, the authors of that paper found is that layer normalization does not use the deeper layers inside the network. So what this graph is basically telling is, say this is layer 0, this is 2, this is 4. If you remove layer 0 from the network, this is the accuracy drop that you get. But if you remove layer 1, you're not getting that big of an accuracy drop. So does that mean layer 1 is sort of unimportant to the network? No. All of the layers help in training, else they are pointless. But layer normalization has sort of a detrimental effect on this. It crumples the training capabilities of the deeper networks, which is not very ideal. And this is a very new field of research. We did not know about this. Our lab, me and another instructor of this course, Akash, actually came up with something which sort of solves this. What we came up with is just don't use layer norms. And it sounds very simple, but we have mathematical evidence to believe that layer norm is not necessary in the later layers. It's okay. This is high level stuff. Don't worry about it. Okay. Oh, good. We are done. Man, that was a big lecture.